Okay, today we are going to talk about chapter 15, which is about multiple regression analysis. If you remember, we talked about single linear regression in chapter 14, and we talked about we have two numeric variables. Typically, we have two variables, and these two variables, we were studying the relationship between these two variables, and one of them was independent, the other one was dependent, or the first one was predictor, the other one was a response variable. And in some situations, we're going to have more than two variables. We're going to have three or more than three. And this is the typical, by the way. The typical, you are going to find that not just one independent variable explains the variation, the whole variation of the dependent variable. No, we're going to find more than one variable that everyone contributes in a specific amount to explain the variation of the dependent variable. Let's look at this example. We have an automobile manufacturer, and they are interested to study the relationship between what? Between the sales, this is number one, and variables that influences the sales. Because I need to know what factors that may increase or decrease my sales, right? Some of these variables are what? The price of the automobiles. This is one of the predictors. The competitors' sales is another thing. How much others sell. Advertising. And like other economic variables like the personal income, disposable personal income, inflation rate, and unemployment rate. Look at how many, let me just change the sales color so we know that we are talking, this is my major. So this is the sales, it's like the dependent variable, and we believe that all of these independent that they may contribute to the variation of the sales. So now how many variables do we have? 1, 2, 3, 4, 5, 6. We have 6 variables, or this person or this vice president, he believes that these 6 variables, they may contribute or influences the sales, the automobile sales, okay? So now we are talking about multiple regression. In the past, if you remember, we had what? We had only single variable, y equals beta naught plus beta 1 x1 only. So what we had a single variable, single independent variable explains some variation in the dependent variable. In fact, if x and y are perfectly correlated, then the proportion explained will be less than, will be 100%. But if they are not perfectly correlated, the proportion explained by the x, by the model or x1 is going to be less than 100%. The bottom line is what? Now we had more than x1. We believe that we have more variables that they may contribute to the variation, to explain the variation of the y. Does that make sense? Again, so this is beta naught, this is beta 1, beta 2, and this is the population model. And as we said, we have assumptions they have to meet. And because we always look at the samples, that's why what we do is we just take a sample and create a model. This is the model, the estimated model regression. And this is the B note, which is the estimated or unbiased estimator of the beta note. And this is B1, which is the unbiased estimator of beta 1. And this is B2, etc., the unbiased estimator of beta 2. And the problem is with this model, we have so many x's, right? So we have so many variables. We have more than 2 variables. If you have 2 variables, you can plot the relationship in the xy plane. If you have 3 variables, you can plot the relationship in the xyz, 3 dimensions. But if you have more than three variables, there is no way to see it, okay? So we call it like hyperplane. So we have multi-dimensional space in this case. So, but we cannot view it, we cannot see it. So the process of creating the model or studying the model is the same, but now we have more kind of variables right now, okay? But the idea is the same. So we have 3 steps we're going to follow. Number 1 is the model specification. Model specification, then model building, then model diagnostic, okay, or diagnosis. So what is the process of model specification? First of all, you have to understand the problem. Understanding the problem is knowing your dependent variable and decide which independent variables should be included in the model. We have to know that the dependent variable. We have to know how many independent variables do we have. And which ones we would like to include, or we believe that they may contribute, okay? After that, we would like to know the sample data that we are going to get. We have to have the sample that is available for all variables. And we have to make sure what? We have to make sure that the minimum sample size has to be number of independent variables plus 1. And this is the minimum. Actually, we prefer to have way more than this. So the larger is the better, okay? This is important. So we're going to solve one example across the board. So we're going to do all of these steps, model specification, model building, and model diagnosis, for just one example, as we did in chapter 14. So what do we have right now? We have an athletic director in a university is developing a multiple regression model, and to be used to explain the variation. Again, we are trying to explain the variation in the attendance at the football games. So this is my dependent variable. dependent variable, game attendance. We would like to build a multiple regression model to explain variation in the attendance at the football games, right? And we have a sample size. We have 16 games. So we collected a sample of 16 games from home games played during the past 10 seasons. So the data for the following factors were determined. So these are the data that we collected. These are the data that we have right now. So we have the game attendance, and the question makes it easy for you. So it says this is why, although it's already explained here. So the game attendance is the game attendance is the dependent variable or the response variable, and we believe that these variables, they may contribute to the variation of the attendance of the games for the games. So team win-loss percentage to date. So maybe if the team wins, we're gonna have more attendance, and this makes sense to me. So this is what I'm projecting, by the way. Opponent win-loss percentage to date. This should be maybe the opposite if it's, right? And the games played this season, number of the games, or the games played this season, and the temperature at the game time. So maybe also here, I may project that if the temperature increases, maybe the temperature plays like, it depends on the place, by the way. It depends on the state. So let's see. So I cannot say anything here because I don't know the state, if it's north or south, or right. So describe the model specification. The model specification, would like to know the dependent variable first, right? The dependent variable. The dependent variable is, just write these down. Dependent variable is game attendance, right? Also, we have the independent variables. So I have all of these, my independent variables. Also, I have what? I have a sample size, 16 games, right? Which is way above the number of independent variables. So this is the description of the model. And you would like to build, the goal is to build a regression model. So the goal is to develop a multiple regression model, okay? Study the variation, or to study what factors helps explaining the variations in the game attendance, okay? So we may say this. After that, we're going to do the model building. So the model building is the process of constructing mathematical equation in which some or all of the independent variables are used in an attempt to explain the variation in the dependent variable. So the question is what we are trying to build here. So let me say this. Let me write this down. We are trying to build the following. So we have the game attendance. We are trying to write this in terms of beta naught plus beta 1 times team win loss team win and loss percentage to date plus beta 1 and opponent, we copy paste here faster, plus win and loss, plus beta 3, beta 2, beta 3, should be 2, beta 3 times the games played in the season. So we have many variables, you see that. Beta 4 plus beta 4 times the temperature. So this is the population model that we are trying to build. And as we said before, we have this, we cannot get the population model, so we are estimating the population model, okay? We are estimating the population model. the estimated model is going to be the estimated game attendance, and we have to add the epsilon, the error here, right? Epsilon, which is the error. But for the sample model, the one that we are trying to build, is we have the estimated game attendance equals B naught plus B1 times the team win plus B3, etc., without the error, okay? Because the error is already included in the model. So what is the correlation coefficient? First, we would like to find the correlation coefficient. So the question says produce the scatter plot for each independent variable versus the dependent variable and create a correlation coefficient. So what I did, actually, I just copied the data into Minitab. Then we go to stat, basic statistics. Then we go to correlation. And we're going to choose everything except let me go back or look at the data here. We have game number. Game number, we have nothing. This is not a variable. This is just an ID, right? So these are the variables from C2 to C6. Select all of them, options. Pearson correlation, fine. Graphs, correlations and intervals, fine. Let's get the pairwise correlation table. So we have the scatter plots here, so we can copy this. And it's not very clear, but we can look at the correlation matrix. But still we can see something. We can see that we have some positive relationship. Look, this is kind of a strong relationship. Okay, so that the titles are merged. This should be a bigger. We can make it smaller, I guess. Anyway, let's not just focus on this. Let me get this correlation. Copy. So I'm going to copy this. This will tell you everything. So the correlations coefficients, which is we can see it in the scatter plot, we can see the following. We can see the following, that mostly we have moderate relationships between, but this one is weak, and it makes sense because they're opposite to each other, right? This one is a strong relationship, is the game attendance and the team winning loss percentage. And it makes sense to me, because if the team wins, so people attends the game. Otherwise, if your team is loser, so you're going to see the opposite way around. And maybe look at the temperature now. The temperature, we have negatives, right? So the negative across the board. So, I mean, if the temperature increases, the attendance decreases, right? So maybe we're talking about kind of south states or something, because it's kind of maybe going in summertime. Let's say this is going to be the case, maybe. But this is the comment. So the comments on the answers, as I said exactly, you have to write something about the relationship between the game attendance and the team win-loss percentage. It seems that we have a strong relationship between these two variables only. Other relationships are okay, and we have negative relationship between the temperature and all of the other variables, including the dependent variable. Okay, remember, the game attendance is my dependent variable, and others are my independent variables. Test for the significance of the correlation, as we said, because this is based on the sample. What we have to do, we have to study the relationship, or we have to create or to check for the significance, right? So to check for the significance, we have to develop the hypothesis. The row 1 equals 0, row 1 is not equal to 0, row 2 is equal to 0, row 2 is not equal to, what is row 1? Okay. The question is, we are studying the relationship between the independent variables and the dependent variable, okay? The independent and the dependent. So I'm going to focus on the first column only. So this represents R. Let's say this is R1. This is R1. Little r, okay? Little r. I don't know why it becomes. So this should be little r, okay? This is R2. This is R3. This is R4. So these are the Pearson correlation coefficients for the sample, and we would like to see whether each of them is significant or no, right? Do you have a significant relationship between them or no? So what you have to do, you have to build all of these hypotheses. This is 2, this is 2. The correlation is 0 between the team winning loss percentages compared with the game attendance, or it's not 0, or I mean, it's significant or not significant, right? The same is applicable for row 2 and row 3 and row 4. So we have to have all of them, right? We have to have all of these hypotheses because we have to study the significance. Once we check the significance, we will be able to answer the question that, based on the correlation matrix developed, comment on whether you think a multiple regression model will be effectively developed from these data. We can say so if we check the significance of the correlation. If we find something significant, then we can say, oh, let's try to build the model, to build that model, okay, to build this model, the estimated game attendance, etc. So let me write the sample model here, estimated without the error. These are B's. So to do this, we're going to go to Minitab and we're going to copy this. Pairwise Pearson correlation, and we have the 95% confidence level. And we're going to ask about I should have said use alpha 0.05. Okay. So look at them. What we care about, the first few, the first 4. So the relationship between the independent and the dependent. So that's why I'm looking for the first 4. So using 5%, this is less than 5%. So this is significant. This is not less than 5%. So this is not significant. So this is not less than 5%. This is less than 5%. This is not less than 5%, right? Did I ask for did I use, let me check. Okay. Because I want to be kind of consistent, right? For the alpha. Yeah. So what we have two, there is a significant relationship between what and what. So let me highlight them. We can say there is a significant relationship between game attendance and team winning, losing percentage and games played. Therefore, a multiple regression model could be effective. So we believe that we might have something. The question is, someone's going to tell me, which is a good question. Do I need to build the model using only these two or all of them? Okay, it's a good question. So right now, I would suggest to build the model using all of the four variables because you have many other measures to conduct. And after that, we're going to comment what to do, okay? So what we're going to do right now, we are going to build the regression model. And again, we have to justify this since the p-value is less than alpha for both of them, okay? For both of them. Oops, okay. Okay, build the regression model. After we said that, hey, we got something, so we might think about the regression model. So what we're going to do, we're going to use the sample data to estimate the multiple regression model that contains all of the variables. Then we're going to interpret the coefficients, okay? So as we did before, we go to stat, regression, fit regression model. What is the response variables? The game attendance. So all of the other variables are continuous predictors. But remember, nothing to do with the game number. Oh, I think I'm going to go with the expanded, okay. Oh, it's so this is my regression equation. This is my estimated or predicted estimated game attendance, right? So let me say something about this, about the coefficient. So the coefficient for each independent variable, this coefficient, this coefficient, this coefficient, and this coefficient, they represents what? These are these representing an estimate of the average change in the dependent variable for a 1 unit change in the independent variable. And this statement is important now. Holding all other independent variables constant. So each variable, we look at the contribution for each variable without having an effect from the other variables, okay? So holding all other independent variables constant. So let me write this. Note that the coefficient for each independent variable represents an estimate of the average change in the dependent variable for a 1 unit change in the independent variable, holding all other independent variables constant. Okay? For instance, we can think about, let's say for the team winning, or let's think about this one. Let's just interpret this one. Okay? So let's keep everything constant. For teams, this is, let me the interpretation. The in of B4, I guess, B3. This is B1, B2, B3, yes. So for teams of the same what? The same team winning or win-loss percentage, same opponent win-loss percentage, same temperature. So we're keeping these constant, all of them constant. What we say then, a 1 unit or a 1 increase of number of games played is estimated to increase the game attendance by 32 games. So per 1 increase of the number of games played will result in increasing number of attendance by 32, not games, persons, right? So number of attendance is going to be increased by 32 people, holding all other variables constant. So we can say it another way. A 1 increase of the numbers of games played is estimated an increase game a one increase of the number of games played is estimated an increased game attendance by 32 persons, holding all other variables constant. So we can say it that way as well, okay? So you can do it this way or the other way around, okay? The same thing with other variables. For example, 1 unit increase of the temperature, 1 Fahrenheit increase in the temperature is estimated to increase the game attendance by 55.5 people, holding all other variables constant. The same thing with the team winning loss percentages. A 1% increase of the team winning / loss percentages will result in an estimated increase in the team game attendance by 63 people, holding all other variables constant. For the temperature, I made a mistake because I just realized that we have a negative here. So a 1 unit increase in the temperature will result in a decrease of the people attending the game by 55%, by 55 people. So we have a decreasing or a negative relationship here, okay? So this is for the interpretation of the regression model. After that, we are going to find, so we are still building the model. We are still in the second phase. If you remember, we talked about, we have 3 phases. We have model specification, model building, model diagnosis. So we're still doing the model building. We're still in the model building process. After getting the regression equation, we interpreted the coefficients, and it's clear that we have some negative, some positive relationships. We need to find the coefficient of determination, right? We have to look at the coefficient of determination, which is the portion that is explained by the model, the portion of the dependent variable that is explained by the model or the other independent variables. Okay, so what we do, we look at this, and I'm going to copy this, the model summary. So the question says, what is the percentage of the total variation in the dependent variable is explained by the 4 independent variables in the model? And the question is technically asking you to find the coefficient of variation. But we have to stop here and talk about something, because this is important now. So the R squared, we have 77.5. So what we can say more than 75% of the variation in game attendance can be explained by the linear relationship of the, how many, we have 4, of the 4 independent variables in the regression model to the dependent variable. Okay, so you have 75% of the variation in the game attendance explained by the linear relationship. So the question is, we have to ask a question here. Are all independent variables equally important to the model's ability to explain the variation? This question needs to be answered. So we need to answer this question. Before we answer this question, I have to make a comment here. We have something called adjusted R squared. Adjusted R squared. So what is the adjusted R squared? It's the measure of the percentage of explained variations. This is here. It's a measure of the percentage of the explained variation in the dependent variable in a multiple regression model that takes into account the relationship between the sample size and the number of independent variables in the regression model. The problem with R squared, by the way, is as the number of independent variables increases, the R squared is automatically going to increase. So this is from the formula itself, okay? So it's always going to increase. So this is not an accurate measure. So to do this, to account for this increasing in the sample size and or the number of independent variables, we have to look at other formula, which is R squared adjusted. So technically, when you have multiple regression analysis, we use the R squared or the adjusted R squared. So in this example, what is the adjusted R squared is 69.3. And now the question is, are all of these independent variables are equally important to the model's ability to explain the variation? The question is no, they are not equally important. Some of them, they are more important than the others. So in this case, we are going to move to something called model diagnostics. Okay, we're going to move to model diagnosis. What is the model diagnosis? It's the process of analyzing the quality of the model. Now we have a model, but we would like to check the quality of the model, how well this model fits the sample data. To do this, we are going to answer 5 questions, but this question, I'm not going to answer it. I'm going to skip this. It's important, but it's not going to be part of the class. So we're going to look at the overall model significance. And this is something we did before for the simple linear regression model. Also, we're going to look at the individual variables. Which one of them is significant in the model? Also, we're going to look at another measure we call the standard error, okay, or the standard deviation of the model, which is the standard error. Is it large? Is it small? Finally, we're going to look at something we call it multicollinearity issue. Do we have a multicollinearity issue? So we are going to define this, okay? So all of these will be discussed in next week, next class. This is it for today. Thank you so much.